In the boundless expanse of space, mysteries await that could alter our understanding of the universe. Every day, scientists make discoveries that pose new questions to humanity, challenging us to reconsider the laws of physics and even the nature of the universe itself. Some of these discoveries are so astonishing that they defy ordinary logic. Imagine an object that defies the familiar laws of gravity and physics. It appears in the depths of space as though created by forces beyond our comprehension. Gazing upon it, you would feel an involuntary wonder. How could such a phenomenon arise among stars and galaxies? What if there is something more behind this enigma? Could it be the key to unlocking the very essence of the universe? Or is it merely a play of light and gravity designed to mislead us? The effect of gravitational lensing is one of the most important phenomena observed in cosmology, and its significance is hard to overstate. It occurs when massive objects such as galaxies or galaxy clusters warp space-time, affecting the light passing by them. The gravity of this object acts like a lens, distorting and magnifying light, which allows the observation of distant cosmic objects that would otherwise remain beyond the reach of modern telescopes. As a result of this distortion, light from distant objects behind massive gravitational structures can be significantly magnified or even altered in shape. Gravitational lenses not only alter the visible appearance of galaxies, but also allow for the study of internal processes occurring within them, such as star formation and the dynamics of stellar systems. This phenomenon allows scientists to peer into farther reaches of the universe than was previously possible, and to study objects that would otherwise be hidden behind dense cosmic structures. The James Webb Space Telescope, with its unique capabilities for infrared observation, has become a powerful tool for studying gravitational lensing. For example, a new image of the quasar RxJ 1131-1231, located about 6 billion light-years from Earth in the constellation Crater, demonstrates a rare gravitational lensing event. Here, the light from the distant quasar is bent by the gravity of a massive galaxy in the foreground. As a result of this bending, the light from the quasar creates a bright arc and 4 separate images of the object, revealing an unusual visual effect. Lensing can increase the brightness of objects several times, allowing for high-resolution images and detailed views of structures that would otherwise be too faint or distant to observe. This image was captured using the MIRI, mid-infrared instrument, as part of the JWST's dark matter research program. The gravitational lensing depicted in the image plays a crucial role in studying not only distant objects, but also the nature of black holes and dark matter. New data provided by JWST will help scientists gain a deeper understanding of the complex processes occurring in the universe and provide new keys to unravel its darkest mysteries. Unlike optical telescopes, which are limited to visible light, Webb can penetrate through clouds of cosmic dust and gas, providing much clearer and more detailed images of objects. This opens new avenues for studying galaxies, whose shapes and structures may be significantly distorted by the lensing effect, as seen with the recently discovered cosmic question mark. This phenomenon not only enhances image resolution but also plays a key role in measuring the mass of galaxies and clusters. The more massive the object, the stronger its gravitational field, and consequently, the greater the distortion it causes in light rays. Moreover, gravitational lensing provides a unique opportunity to study the distribution of dark matter, which is revealed through the distortions created by its gravitational influence. The gravitational lensing effect serves as a kind of natural telescope, amplifying the capabilities of artificial instruments like Webb. However, studying lensing also faces certain challenges. One of the main tasks is interpreting the data, as distortions can be extremely complex and layered. The interpretation of effects related to Einstein's ring is particularly challenging. This phenomenon occurs when light from a distant galaxy is distorted into a ring or arc shape due to a massive object located between the light source and the observer. This effect, first predicted by Albert Einstein in 1936, results in the formation of an isometric ring around the lensing object if the observer, the lensing object, and the light source are aligned. This requires the use of sophisticated mathematical models to unfold distorted images and reconstruct the true shape of galaxies. The Einstein ring effect, as demonstrated by the ring B 1938 plus 666, with a diameter of approximately 1.9 arc-seconds, provides scientists with valuable information about the mass distribution and structure of lensing objects. In this context, each new case, such as the question mark, adds important details to the overall picture. What else might be hidden behind these distorted images, and what mysteries does gravity continue to conceal from us? The cosmic question mark, recently discovered by the James Webb Space Telescope, is one of the most intriguing finds in modern astronomy. Although this region was previously observed by the Hubble Space Telescope, it was only Webb that captured the dust-red galaxy, forming an intriguing question mark shape. It has drawn attention from scientists due to its size and the variety of details, including its mysterious figure. Its shape resembles a question mark, which alone evokes associations with the mysteries of space. But what exactly is hidden behind this cosmic question mark? What is the nature of the strange object in the composite image of Herbig-Haro 4647, obtained using the James Webb Telescope's NARCam? Experts from the Space Telescope Science Institute, STSCI, in Baltimore, Maryland, provided more details. This question mark-shaped object is likely a pair of distant galaxies in the background interacting with each other. During their approach and collision, their shapes might become distorted, including the ejection of elongated gas jets, explains Dr. Christopher Britt, a staff member at STSCI's Office of Public Outreach. The reddish color of this object indicates that the galaxies are at a significant distance from us and exhibit a substantial redshift. Scientists from the Space Telescope Science Institute, STSCI, including Frank Summers, Roland van der Marel, and Gottina Besler from Columbia University, have created a visualization that illustrates a possible scenario for this merger. The head-on collision is expected to lead to the formation of a new, massive elliptical galaxy. However, this event is unlikely to have any significant impact on Earth if it still exists 4 billion years from now. For scientists, this object represents not just an interesting visual anomaly, but also a valuable source of information about gravitational interactions on a galactic scale. The cosmic question mark prompts researchers to formulate new hypotheses about how galaxies interact and how gravity may influence their structure. Many questions remain. How exactly did these galaxies interact? What role does dark matter play in the formation of such complex gravitational effects? And is it possible that this discovery is just the first of many similar findings in the future? Intergalactic interactions play a crucial role in the formation and evolution of galaxies, and observing them provides insight into the dynamics and scale of processes occurring in the universe. When two galaxies approach each other under the influence of mutual gravitational attraction, their collision can lead to complex and varied phenomena. In the case of the cosmic question mark, this interaction has become a catalyst for creating a distortion resembling a question mark symbol, which scientists have observed. Galaxy collisions typically occur over millions, and sometimes billions of years. They do not always result in immediate destruction or merger. Instead, gravitational forces cause galaxies to dance around each other, forming elongated structures such as tails, bridges of stars, gas, and dust, and distortions similar to the question mark observed. These deformations can significantly alter both the appearance and internal structure of galaxies, and in some cases, even trigger active star formation processes. Galactic interactions are not limited to just mechanical collisions. The influence of gravitational fields extends far beyond visible matter. One such effect is gravitational lensing. Additionally, these collisions often lead to the redistribution of mass within galaxies. Gravitational forces cause the movement of gas and dust, which can lead to the formation of new stellar systems. Studying these interactions also provides an opportunity to assess the distribution of dark matter. Although this matter is invisible to telescopes, its presence can be inferred from gravitational effects on light passing through it. Intergalactic interactions open many questions for scientists. How exactly does the distribution of dark matter influence such collisions? What other forms of galactic interactions can we expect to observe with advancements in technology? The importance of the discovery of the cosmic question mark lies in its potential to expand our understanding of gravity and interactions on galactic scales. This discovery demonstrates how powerful gravitational effects can be when dealing with massive structures like galaxies. The question mark shape is not just a visual anomaly, but the result of complex, multi-layered processes that scientists continue to study. Analyzing these processes may shed light on fundamental aspects of cosmology, including the nature of dark matter and energy that shapes the structure of the universe. Studying such objects offers a new perspective on the distribution of matter in space. One of the most significant challenges astronomers face is understanding how gravitational fields affect both visible and invisible matter. In the case of the cosmic question mark, its shape and structure might have been caused by large volumes of dark matter, which, although invisible to our eyes, exerts colossal gravitational influence on surrounding objects. Dark matter is estimated to constitute about 85% of the universe's mass, but its nature remains a mystery. In addition to dark matter, dark energy plays a crucial role in such interactions. This mysterious form of energy is responsible for the accelerated expansion of the universe and likely affects gravitational interactions on large cosmic scales. Although scientists are still unable to precisely determine how dark energy relates to the formation of structures like the cosmic question mark, further research will help better understand its role in the evolution of galaxies and the universe as a whole. Each new discovery like this provides scientists with more data to build more accurate cosmological models. Studying gravitational interactions can help address fundamental questions about how the first galaxies formed after the Big Bang, how the structure of the universe evolves over time, and what the future holds. With advancements in technology and increased observational precision, scientists can delve deeper into the mysteries of space, gradually uncovering its most complex and intriguing aspects. Yet, the question remains, can such discoveries be the key to a more global understanding of the universe, or do they hide even more complex and unresolved mysteries? The role of the James Webb Space Telescope is extremely significant in the study of cosmic enigmas and similar phenomena. This instrument, designed to operate in the infrared range, ushers in a new era in astronomy. Unlike previous telescopes such as Hubble, Webb can peer through clouds of cosmic dust and observe objects that are at enormous distances from us. Thanks to its incredible sensitivity to infrared radiation, scientists can obtain higher resolution images and study details of galactic interactions that were previously hidden. Infrared observations are particularly important for studying distant galaxies and cosmic structures because, as distance increases, the light emitted by objects shifts to the red end of the spectrum. This phenomenon, known as cosmological redshift, is related to the expansion of the universe. The farther an object is from us, the more its light shifts into the infrared range. This is why the James Webb Space Telescope was designed to work in this range, allowing scientists to explore galaxies that formed shortly after the Big Bang. The study of cosmic enigmas with Webb has provided detailed data on distortions caused by gravitational lensing and examined galactic interactions at a completely new level. While previous observations made by other telescopes could capture the general outlines of interactions, Webb allows for the observation of the finest details of these processes, including the precise distribution of stars and gas, their movement, and the intensity of star formation in merger regions. Such a level of detail provides unprecedented data for modeling and understanding how these processes occur. Moreover, the James Webb Space Telescope helps address one of the greatest mysteries of cosmology: the distribution of dark matter. Although dark matter cannot be observed directly, its presence can be detected through gravitational effects, such as the lensing of light from distant galaxies. Webb, with its high sensitivity to light variations, can detect even faint distortions caused by dark matter, allowing for a more accurate assessment of its quantity and distribution in space. This data can offer crucial insights into how galaxies form and what forces govern their evolution. The telescope also provides the opportunity to observe the early stages of galaxy formation, when the first stars were just beginning to ignite. This critical moment in the history of the universe known as the reionization epoch, occurred when ultraviolet light from the first stars began to ionize the surrounding hydrogen, making space more transparent to radiation. Thanks to Webb, scientists can see how these primordial stars formed and what processes may have initiated the formation of complex structures, such as galaxies. Astronomers from the University of Cambridge, using the James Webb Telescope, conducted a detailed study of the galaxy GNZ 11, one of the most distant known to date. Utilizing two highly sensitive near-infrared instruments, the NIRCam camera and the NIRSPEC spectrograph, the researchers discovered traces of third-generation stars. However, their existence was brief, making their detection in the present universe significantly challenging. To investigate such ancient objects, it is necessary to look into the distant past, which the James Webb Telescope enables. Despite its incredible capabilities and the size of the first stars, it is impossible to detect individual stars. Nonetheless, researchers managed to find a concentration of ionized helium on the periphery of the galaxy GNZ 11. This concentration resulted from the ultraviolet radiation emitted by the earliest stars. Each new discovery made with the James Webb Telescope opens new horizons for understanding not only individual galactic objects but also the entire history of the universe. What other mysteries lie hidden in the depths of space that will become accessible thanks to its unprecedented resolution? The cosmic question mark is not only a fascinating phenomenon that attracts attention with its unusual shape, but also an important object for in-depth scientific research. Its study allows astronomers to draw key conclusions about the structure and evolution of galaxies, as well as about processes occurring on a cosmic scale. However, to fully uncover the mysteries of such objects, the use of the most advanced technologies and observational methods, which are constantly improving, is required. The James Webb Space Telescope, along with other instruments, provides us with the opportunity not only to view distant corners of the universe, but also to delve into the study of processes that were previously beyond our understanding. Each new discovery expands our knowledge of galactic dynamics, the interactions of matter and energy, and the gravitational effects capable of altering the path of light and space. It is possible that interactions like those observed in the cosmic question mark were involved in the formation of our own Milky Way galaxy. Modern cosmology faces a number of unresolved questions that remain beyond our current knowledge. Objects like the cosmic question mark force us to rethink many established concepts: gravitational lenses, galaxy interactions, and the influence of dark matter. All these aspects represent just the tip of the iceberg in the infinite cosmic ocean that humanity continues to explore. Each new observation or experiment involving the James Webb Space Telescope brings fresh insights into the structure of the universe. But this is just the beginning. The future of astronomy promises even more discoveries that may change our view of the very nature of space. With every new step, scientists move closer to answering questions that have troubled humanity for millennia. How did the universe begin, and what are its ultimate boundaries? To stay updated with the latest news from the world of space and be among the first to learn about new discoveries, subscribe to our channel and follow our updates. The universe continues to amaze, and even more mysteries await us to unravel.